Hello everyone, I am Derisa and I'll be presenting my paper on practical incident response framework for generative AI systems. So let me start with a question. When a normal application is compromised, most of us roughly know what happens next. We preserve the evidence, scope the blast radius, contain the host, rotate credentials, patch, recover, and write a post incident report. Now imagine the same incident, but this time the compromise is not a host but a conversation. The exploit is not a binary but instead a prompt, and the persistence mechanism is not a register key or a cron job, but instead it's a poisoned PDF in the retrieval pipeline waiting for the model to read it. That is the problem that I want to talk about today. Incident response for generative AI system, not say AI security in abstract or a list of risk, but a practical question. When the model in production fails, who does what, in what order, with what evidence, and under whose authority? So, going ahead to the context and the urgency, generative AI adoption is no longer pilot projects. It's into enterprise workflows, and it's like the perfect storm: rapid adoption, rising incidents, and poor operational readiness. The adoption has reached 71% in 2024 itself, and the incidents are raising to 56.4%. The knowledge gap sits at 65%. Many security professionals acknowledge that they don't feel ready to acknowledge failures of generative AI systems. So the crisis is real. However, the gap matters because organizations are increasingly putting LLMs into their customer support, internal knowledge retrieval, software engineering, HR fraud analysis, and decision support workflows. This is no longer just a security problem, but also a regulatory urgency. The EUAI Act mandates that serious incident need to be reported within 15 days of awareness or sooner, depending on the severity of the incident. Going ahead to the research gap. For decades, the NIST SP 800 and ISO 27035 have been a bedrock of incident response, providing structured framework how to respond to incident. However, these frameworks have been largely for infrastructure failures, which are largely deterministic. GenAI is different. It's no longer deterministic but probabilistic, and they're ambiguous and often application layer failures. The same prompt may not always give the same output. The indicators of compromise are completely different, like conversational patterns, and the root cause may sometimes be model behavior or retrieval context or third party data or tool permission. This is what I'd like to call as the operational synthesis gap. We have the strategic layer, we have the NIST AI RMF 600, and we have the regulatory principles. We also have the tactical layer. We have the OWASP LLM for top 10, the MITRE ATLAS techniques, and public incident reports. However, what we lack is the operational layer, a structured, repeatable, auditable playbook that exactly tells the incident team what to do in the first 15 minutes, in the first hour, and in the post incident review. How this research contributes is creating of a response-centric taxonomy. So when we speak of this response-centric taxonomy, instead of classifying incidents only by the vulnerability type, the framework classifies them by response workflow. This matters because two attacks may look completely similar technically but require completely different containment paths. One such example is direct prompt injection and indirect prompt injection. In direct prompt injection, generally we isolate the user session and patch input filters. However, in indirect prompt injection, we need to block the upstream data source, flush active context, and investigate the entire data supply pipeline. So, same family of risk, however, completely different operational workflows. And this is the central idea behind creating archetypes based on similarity of containment instead of risks. Going ahead to the methodology used, so the first phase of this playbooks was categorization. So the postmortems of incidents occurring from 2023 to 2025 were analyzed using thematic clustering, and these have been clustered by response workflow similarity using the design science research framework. And further, the playbook artifacts have been designed. So the dual traceability matrix approach has been used to provide a red team perspective. Here, if I go to the playbook, so as you can see, this is the red team perspective. That is the threat and vulnerability matrix. Uh, Direct prompt injection and jailbreaks. This is the first archetype. And the MITRE ATLAS techniques and tactics are mapped along with the OWASP LLM vulnerabilities. And one such real world anchor is the skeleton key jailbreak. Sorry, I was not sharing this playbook. Yeah, so as we can see, this is the red team perspective, the MITRE ATLAS tactics mapped, and the OWASP LLM vulnerabilities for direct prompt injection and jailbreaks. And if we go to the blue team perspective, that is the incident response framework, we can see that this is the phase checklist having all the steps for incident response mapped to NIST AI 601. And the next phase was evaluation of this playbook against echo chamber jailbreak scenario, which included real world practitioners and mixed methods of data collection to evaluate its effectiveness for GenAI incidents. The six GenAI archetypes. Based on the containment workflow similarity, we categorized these GenAI incidents, first being the direct prompt injection and jailbreak. Here, the user directly manipulates the model through input, often trying to override system instructions or safety controls. One classic example is the Bing skeleton key jailbreak. The containment path is to isolate the session, block the user or source, preserve prompts and outputs, and deploy emergency filtering. If we look at indirect prompt injection, one case in point is Grok anti-Semitic rant in 2025. Here, the malicious instructions are generally hidden in the upstream data sources such as PDFs, web page, RSS feed, or RAG documents. The response is different. It's not just blocking the user. We have to trace the output back to the poison source, block the source, purge active context, and clean the ingestion pipeline. The third archetype is sensitive data leakage. Here, generally the LLM, due to cross-tenant bugs or model memorization or miscode retrieval, often exposes PII or proprietary information. Due to leakage of PII information, as it happened in ChatGPT history leak in 2023, it triggers a regulatory and compliance notification clock. Here, the containment involves legal and data protection team to be involved, and that is what makes this containment distinct from other attacks of other model failures. Then the fourth archetype is model or data poisoning. This involves compromised model weights, tainted training data, or malicious embeddings entering in the AI supply chain. Containment requires taking the model out of production, then isolating the CI/CD pipeline, preserving the compromised components, and rolling back to a trusted golden copy. Going ahead to the fifth archetype, that is the plugin and toolchain abuse. One classic case in point here is the vibe coding incident that happened in 2025 due to excessive autonomy. A live database was deleted in production, and this is very much in line with agentic AI, which is widely in use now. This is generally where external tools, API plugin, or agent capability is abused to take unauthorized downstream action. And the response centers on revoking credentials, disabling integrations, and sandboxing the abuse services. Going ahead to resource exhaustion. Here, this is similar to the DOS attack that is there in traditional attacks, but only on LLMs. This includes token flooding, API key abuse, and LLM jacking style cost attacks. The response is financial as well as technical, as they need to be throttling of tokens, rotating credentials, freezing cloud spend, and engaging with the cloud provider. The design choice is simple, but it is important as the similarity in response workflow will actually help in responding to incident in a structured way. The standards integration is a deliberate design choice, as most of the playbooks are either too generic to act on or too operational to satisfy governance and audit requirements. This framework tries to bridge that. It uses the dual traceability matrix. The first matrix is the threat and vulnerability matrix that I had presented earlier. I'll present it once again. Where we map the threat and vulnerabilities like the MITRE attack tactics and techniques and the OWASP risks. And the second phase is the incident response traceability matrix, where all the actions of incident response as per like preparation phase and detection phase. So all these phases are mapped directly to the NIST AI 600 mappings, as well as the owners of every stage or every action that is to be taken, the decision gates. So, in case if there's a audit and if the auditor asks why a certain step was taken, we can directly point it to the evidence to the owner and its standard mapping. Going ahead to the components of the playbook. So, the playbook, that is the incident response workflow, has the phase checklist, the RACI matrix, and the Swimlane diagram. So, the phase checklist has all the six phases of incident response, that is, preparation, detection and analysis, containment, eradication, recovery, and post incident review. Each phase uses a seven-part structure, that is, the objective, input triggers, actions, decision gates, communication, evidence, and output. So let's go ahead to have a look at that. As we can see, this is the phase checklist, the preparation phase, the objective, that is establish, prevent, control to minimize the likelihood and impact of prompt injection, the input triggers, and then we go to the action step checklist where we have the owner and the NIST mapping, the decision gates, the owners, the communication hook, the preparatory artifacts. And as we proceed to the detection and analysis phase, we have the exact same structure to make it structured and auditable and repeatable. We have the actions, the owners, the mappings again, along with the decision gates, like whether how to determine the severity of the incident, the forensic acquisition scope, the regulatory reporting, the communication hook between team members and the channel, the content focus, the evidence that needs to be collected, session and correlation logs, incident declaration record, prompt and output logs, blast radius report, regulatory assessment, business impact assessment, chain of custody, and same with the containment. We have a structured workflow here as well. The actions of containment, as in preserve volatile evidence, deploy emergency filters, scan for widespread exploitation, execute strategic containment, the decision gates, like if the account or the session is to be terminated, the scope, the emergency filter deployment approval, the owner, the trigger, and the communication hooks, the evidence that needs to be collected. And moving further, it goes to the eradication phase, like developing permanent filters, executing model rollback, validating patch remediation, and followed by the decision gates, purge versus amend context, model rollback versus patch forward. the communication hooks, and the evidence that needs to be collected. And similarly, for the recovery phase, so this employs a daisy chain logic which builds a very repeatable structure that reduces the cognitive load on the incident teams during an incident, and helps respond in a disciplined way, in a very structured way. And this is for the post incident review, the communication hook, the documentation, and the output. Going ahead to the RACI matrix, so every steps are tracked into RACI matrix with target SLA windows. This will help to determine the mean time for detection and mean time for recovery. And this is not acting just as a matrix but a performance management tool during a live incident, as all the steps are directly mapped. Everybody who is responsible, consulted, informed, or accountable is traced into this. And going ahead to the swim lane diagram, so this is where the handoffs between different team members at every stage are clearly visible, and the ownership and dependencies can be mapped quickly during a crisis. This the value of swim lane diagrams is not artistic but rather cognitive, that aids the incident response team, as decisions are also mapped. So this has been the structure of the playbooks, the phase checklist, the RACI matrix with the MTTD and MTTC, and the swim lane diagrams with the multidisciplinary roles and the handoffs and the decisions between them, and the dependencies. This helps in cross-functional coordination, helps to make the playbook auditable and defensible, and reduces the cognitive load on the response teams. If we go ahead to understand the validation or the coverage of this playbook with a practical incident, so the incident in context here is echo chamber jailbreak scenario, which is a multi-turn, multi-attack context poisoning that overrides the controls of the model. So, if we see all the phases of incident response and the playbook steps, does the playbook provide a procedure for initial detection, evidence collection, and formal incident declaration? Which is, if we can see the coverage assessment, it's covered, and the actual steps that are mapped. So, this playbook has an entire coverage for every phase of incident response, and if we can see it here, retrieve session logs, confirm policy violation, declare incident, active full IR team, classify multi-ton context poisoning, jailbreak. So these are the detection steps. Similarly, if we go to containment, so does the playbook have procedures for immediate tactical containment and preservation of volatile evidence? Yes, the steps are listed here, and strategic containment actions, which we can see here: terminate session, block account and source IP, capture immutable forensic snapshots, deploy emergency filters, block narrative framing patterns. If widespread, take LLM application offline. And similarly, for eradication, uh, formal process for developing, validating, and deploying a permanent patch. This has been covered in the playbook, and mandating the cleansing of malicious content and a final verification scan. If we can see, the steps are listed here: develop permanent patch, multi-turn isolation guardrail, red team validates fix against echo chamber variants, deploying validated patch via change management, and purge biased outputs from logs and RAG datasets. Same with recovery and post incident review, the phase restoration with heightened output monitoring and confirming 24-hour stability, no re exploitation, final communication to stakeholders, root cause analysis, plus updating the playbook with echo chamber detection signatures. The empirical evidence of the usability of this playbook across a diverse range of practitioners, ranging from incident commander to ML engineers and legal team. This playbook makes the interpretation accuracy faster, which range to 98.80% with a very less error rate of 120% due to its easy to use and easy to read structure. The efficiency, comprehension efficiency was 5.3 minutes on the average, and the system usability score sat at 86.43%. Uh, the responders, I mean the evaluators, said that the immediate structure eliminates guesswork and actionable steps are helpful in navigating the next steps during an incident. Recommendation for organizations: how can these playbooks be adopted? So when a failure, model failure, or a Gen AI incident happens, the question shouldn't be what framework does it belong to. It should be what response path does this require. So the incident response team can adopt these playbooks as per their necessities, depending on their team size, their model architecture, and regulatory exposure. This can also be a blueprint for store automation. As this playbook have clear input and output triggers, this can be embedded into the detection logic of a SOAR platform to automatically respond to such GenAI incidents. SMEs can also adopt these playbooks, and the important part here is preserving the decision gates, evidence requirements, and escalation path. This playbook is not intended to be just a static document, but instead a live process by integrating this into the CI/CD pipeline, so that the feedback loop will continuously and iteratively keep refining the incident response process by using automation. Limitations are acknowledged for this research as this was a part of an academic research. The validation of this playbook was in a simulation rather than a real world live fire incident. So, further research of this incident response for generative AI system can be done through validating them in the real live incident and as per the diverse context of large scale enterprises and SMEs across different sectors. Another limitation is Gen AI threats, as we know, are always constantly evolving. This is a dynamic threat landscape. So now we are having multimodal systems and agentic workflows. So this is not meant to be a static framework, but it needs to be kept updated as per the latest attack surfaces that we come across, just like OWASP and MITRE, which are community efforts at uh, updating these frameworks and making them more usable to the current threat landscape. This is an example of a prompt injection run card, indirect prompt injection that can be used in live fire incidents to respond to Gen AI failures. So, to close this presentation, I'd like to say that incident response has been a discipline that has been helping respond to incidents of infrastructure failures, and the same discipline can be extended to generative AI failures. Even if they look different from traditional incidents, the goal is not to predict every possible jailbreak or poison document in the model. However, the goal is to build a response muscle: clear archetypes, clear ownership, clear evidence, and clear containment paths that improves the system after every incident with a iterative feedback loop. So this is how we move from AI security as a set of warnings to a response as an operational capacity. Thank you.